On for the rest of the week is, of course, that tomorrow is Thursday, so we have a test on chapter, is it 23 and 22 and 23 or and 23. Then on Friday we'll have lecture and we'll start in on reactions. And then Monday we'll have lecture and we'll finish up reactions. And so that means that probably on, depending upon how we cover things, either Thursday or Friday we'll have another test right away, because we've been kind of stretching out some things. We've been going a little slower than normal, and really we've been just pushing the test out a little further than it should be every time. So Thursday and Friday we'll have a test on 24 and 25, because we're going to do the naming from 25 today, right? Because you guys said too many new reactions would confuse you. And then we will bust through the reactions on Friday and Monday. And I might even try to go and cover them all on Friday and then review them on Monday after you've all had a chance to look at them, and do it that way. And then we'll do it that way. And so today what we're basically doing is just looking at naming for chapter 25. And then we'll start thinking about some review for the test. This evening I have dinner plans at 5-ish until whenever, I don't know. So make sure you ask your questions before 4:30-ish. And then I don't know if I'll come back up in the evening or not.
Dinner plans at 8?
No, it's not a date. What? No. It's a friend and her husband and her daughter and their dogs invited me over because they like Lucy. I think it's more about the dogs than anything. No. Anyway, Lucy has lots of friends. More than I do. I know, I'm just saying she has lots of friends. I don't have very many. Oh yes, so it's either, I can come back at 8 or I can bake cookies at 8. I don't know. We'll see. Maybe I'll bake them. Maybe they'll have to wait till Friday. We'll see. So anyway, going on topic. We want to talk about amides and amines. And this is our first functional group that's going to introduce something with nitrogen in it. So an amide is like a carboxylic acid, but instead of a OH group, it has an amine group, an NH2. So this is what we're talking about as the functional group. And so it's got a carbonyl carbon. It's got what we call an amine. And then if we put those things all together, that's what we're calling our amide. And I think it's weird. Your book actually talks about and does amides before it does amines, but it makes more sense for me to think about doing amines first, because amines look an awful lot like alcohols, except with an NH2 group. And so amides kind of look like carboxylic acids, or they can look like esters if we have something attached to those instead of a hydrogen, just like an ester. So when you're thinking about chemical reactions, we're going to remember that amines are an awful lot like alcohols when we eventually do the reactions. And when we think about amides, they're going to have much the same reactions that carboxylic acids and esters do. So sticking the chapter on carboxylic acid, esters, amides, and amines all together on a test kind of makes sense, since there's an awful lot of overlap. It's kind of like the same thing with alcohols and aldehydes and ketones, since a lot of times alcohols get turned into aldehydes and ketones. So how are we going to name these puppies? So for amides, what we're going to do is we're going to change the E to the word amide. I think it's kind of the funniest one, because it's like, wow, that's so logical, isn't it? Like alcohols, we just use an OL, aldehydes are just an AL, a ketone is an ONE, but for amides, we just decide, let's just put the word amide in there. So if you can't identify an amide based on its name, oy, You'll have lots of problems. Now, the other thing is notice that it's always at the end, like a carboxylic acid. Therefore, there's no need to number it or have a location in it. So, you know, one of the things that's confusing after a while sometimes is whether we need a location or a number for a functional group or not. So kind of keep in mind which ones do and which ones don't. And really the deciding factor is if it's stuck at the end of the molecule, it doesn't need a number. And if it can be anywhere else in the molecule, then you can put a number on it. So what would we name the easiest one? Not the easiest one we can draw, but just I picked a random length. So that would normally be 4 carbons is butane, right? Instead, this is butanamide. And if we have any functional groups on there, we always count again from the amide end. And so we have to go 1, 2, 3, 4, 5. So we'd say 4,4-dimethyl pentanamide. So none of the real rules change. As far as, you know, if I've got 2 of them, we'd call it pentane diamide. We number from the functional group and things like that. The thing that's a little bit unique about them is, like esters, we can have things attached to those nitrogens. So before it looked more like a carboxylic acid because it was just at the end, but what if I, for instance, put an ethyl group on that nitrogen? Now we kind of name it like an ester, kind of not. It's actually easier if you ask me. We just call this N-ethyl, and then what did I do, a pentanamide? Pentanamide. So we just simply say that it's attached to the nitrogen on that molecule. And of course, we can have more than one group attached to that nitrogen because it can form up to 3 bonds and still have that lone pair of electrons. So for instance, if I stick an ethyl on there and I stick a methyl on there, then that's just N-ethyl dash N-methyl, bless you, Jess, pentanamide. Notice that we still put it in alphabetical order. Ethyl comes before methyl. And that N is kind of like a number in that, you know, we have to give the location. So it, you know, it's not a number, but it behaves like a number. But it does have one difference from numbers, because where numerically does an N go? Does it go before numbers, after numbers, things like that? Turns out that if we have a bunch of numbers and N's mixed together, the N's always take precedence. So for instance, if I put a methyl group here and an ethyl group there, then when I'm naming this, I start off with the N's, so N-ethyl, N-methyl, and then it's 3-ethyl dash 4-methyl. Wow, this is a name and a half. Pentanamide. So notice that the N's always go first. And notice that they also violate, kind of, the alphabet rule. So the alphabetically. In that we don't say, for instance, N-ethyl, 3-ethyl, N-methyl, 4-methyl. And we don't group numbers and N's together. We don't say, for instance, N3-diethyl, N4-dimethyl. So the N's are completely separate and have their own kind of set of rules. And they always go in the front of the molecule, and the N's by themselves are alphabetized, and then everything after that is alphabetized separately. You guys with me on this? So the ends break the rule. Nitrogen just isn't a class by itself. I should also point out that it's always good to show that little lone pair on it. And in general, what I recommend is if nitrogen has a hydrogen attached to it, I want you to show it. So notice if it's got 2 bonds, it's got no hydrogens attached to it. But if it's only got a single bond like that, I have to show that hydrogen. And that's going to be important when we're talking about chemical reactions and trying to keep track of things. So it's a good habit to get into. It also makes sure that you can count to, 8 electrons if it makes 3 bonds and has a lone pair of electrons drawn on it. So maybe I should even be good and say, okay, let's go back and make sure I drew all my lone pairs in, because J can be a slacker. Now this is not one that we covered when we did chapter 20, but thinking back, you guys should be able to kind of come up with a plausible name for that. If that was a carboxylic acid group, we'd call it benzoic acid. What do you think we call this? What? No, that's a good name, but it's called benzamide. Let's see, am I missing anyone? And it, of course, follows all the normal rules. So just as a friendly reminder, anytime you've got an aromatic in there and you've got, say, something like this, and then say I have a methyl group down there, what have we got to name that? Yeah, orthometa-para. So in this case, it's meta-methyl benzamide. So just a reminder, don't forget your OMP, your ortho, meta, and para stuff if you run across any ones of those on the test, because aromatics are fair game on any test as long as they have the functional group of the chapter we're in, even if we really kind of covered them somewhere else. Let's see, do we want to cover that? No, we'll save chemical properties for separate. And we'll go talk about amines. Amines are kind of like amides. They've got that NH2 group in them. And they're kind of like alcohols in that, that NH2 group can be anywhere on the molecule. So when we name them, we're going to take that E and we're going to call it amine. And maybe they did it because, OL makes sense for alcohol, kind of. But if we did amine, you can't use the ending, and in the AM, the beginning, we would call it like pentanenem. Yeah, maybe it's better to just use amines. And because it can be anywhere, we need a location. Because it can be anywhere. So that's a nice simple one to start with. Instead of ethane, this should be ethanamine. So ethanamine. They kind of roll off the tongue after a while. And we do have to make a distinction, for instance, between that versus this, because remember, amines can be anywhere in the molecule. So this is 1-butanamine, and this is 2-butanamine. And since it's like an alcohol, it can be anywhere in the molecule. What else like an alcohol do you think it possesses? For instance, we can call this a primary amine, a secondary, wait. I'm lying. Go back on that. Okay, so amines have to have the numbers somewhere. They take precedence, so even if you have something like this where you've got an NH2 and say a bunch of chlorines over here, we still start numbering to give the amine the lowest number. So we would call this 5,5,5 trichloro-2 pentanamine. So remember, whatever functional group we're talking about, whatever's the flavor of the month, we have to give the lowest possible numbers, right? And then just like amides, because I've got a couple extra hydrogens there, and it's kind of like not an ester, an ether if you think about it, you can have more than one thing attached to that nitrogen. So there, notice I've got an ethyl group, and then notice that there is a 5-carbon chain. So the longest chain is what we call our main chain, obviously, and the shorter chain is our side chain. And so we would call this N-ethyl dash 2-pentanamine. And then that N behaves just like anything else, meaning it violates all the rules for alphabetization and stuff. It's always on the front of the molecule. So if we have something like this, so here's 1, 2, 3, 4, 5, 6. I've got an ethyl group there. Then we call this N-ethyl dash 2-ethyl dash 3-methyl dash 1, and I ran out of room, so we'll put the hexanamine down below. So again, all the N's, anything attached to that nitrogen that's not the main chain, just goes straight out in front, and it has its own little alphabetization section, and then the other one has its own little alphabetization section. Now, I have to be honest, if you run around the internet enough, you will find people that misname those or have different namings for them. And in fact, with the whole new IUPAC rules, if your book ever switches to it, I have a lot of work in front of me for changing everything. So again, if you check the internet out and it gives you a slightly different name, you know, where they actually alphabetize it properly, just realize that's the new set of rules. Don't sweat it too much. We're just going to stick with the nice simple set of rules that your book kind of simplifies it down to. Now, one thing that can be tough for things like this is if I have a lot of side chains on it. Oops. Here, we'll make this bond extra long. Which one's the longest chain? Sometimes it can be a little tough to tell, right? I can tell that it isn't this one because that's 5, and this one is 1, 2, 3, 4, 5, 6, and this one is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Phew, that was close. If I'd drawn 11, I don't know how to name 11 carbons. I think it's, let's see, decane, and then it's an undecane or something like that. But frankly, it's been so long since I tried to name something with more than 10 carbons, I've forgotten. So let's see, 1, 2, 3, 4. So we would call this 5, oh wait, 6 hex. Hex comes before pent, right? So this would really be a N-hexyl. Oops. Wow, that seems weird because we don't see the big side chains like that very often, do we? N-hexyl, N-pentyl, dash 4 decanamine. Because hex comes before pent. So we still alphabetize it, but what I was saying is that if I have, like for instance, if on that 10 carbon chain I had an ether group someplace, we wouldn't start with the ether group in the name because the N's go first and then we worry about the alphabetization. So the N's always go first, they're alphabetized. The rest of the numbers go where they go, they're alphabetized like normal too. And then the thing is we just don't combine N's and numbers, even though to me that kind of makes sense. It'd be okay to say NN23 tetramethyl something or another. I think there's nothing wrong with that name, but whatever, I don't make up the rules. As a quick reminder for, you know, our regular test, what happens if I have two functional groups? Yeah, so this is just 2, 4, let's see, it's a 5, so pentane diamine. And so we put in a di or a tri or a tetra in there. And then that di goes kind of where that functional group is, right? So the di is saying I have 2 amines. And then using these rules, if I have an amine group and say a carbon-carbon double bond, what's more important? Yeah, the amine, so we go like this, and so we name this as, let's see, 4-pentene dash, we got a 2-amine. And so if it's a double bond and there's 2 functional groups, we usually can squeeze it in there like that, right? And so sometimes you got to be really careful. There might be an extra number around, and if it looks like there's an extra number around for something, realize that you should probably be looking to see if there's a carbon double bond or a triple bond someplace in there, right? Oh yeah, in this case we probably should. Sorry. And again, that one is one of those ones where with the new rules, they change that. So if you do see something, like for instance, under the new rules, this would be pent dash 4-ene dash 2-amine. I actually kind of want them to change to the new rules because that makes a heck of a lot more sense to me, doesn't it? That way the 4 is right where the ene is and the 2 is right where the amine group is.
How do you want us to write it though?
Oh, you used the rules in your book because I decided it's not worth having a separate thing. That, and I'll be honest, I would look forward to the day when they switch to the new rules, but I also dread the day when they switch to new rules because do you know how many molecules are on my computer that I have to rename? Oh my God, it'd be like starting over. I mean, there's probably just at least a couple hundred, if not 1,000 molecules that I'd have to go and rename according to the new rules. So as much as I want them to switch because I think it's better, until your book actually switches, I won't do it because it'll be confusing. Because if someone actually reads the book. I've had people do it in the past. It's scary. Let's see. Other things that we can throw in to both as kind of reminders and things. Going back to chapter 20 again for aromatics, there was one that you were supposed to memorize. This is aniline. Oops. Aniline. I think it's that way. Or is it 2 I's? Now I'm second. Yeah, I think it's 2 I's. That doesn't look right. So my old notes have it wrong. Aniline. You see, I told myself to start pronouncing it aniline, like extra pronounce the I, so that when I spell them that way, I'd get it right. And this should be fresh in your mind, but what the heck? If I had do something like this, what's this? O-ethyl aniline, right? Because they're right next to each other. Oh, let's see, what else can we do to throw you tricks? Also be careful. If you're not paying attention and you're going too fast, you can do silly things like this. What would this be called? Oops, NH2. No double bonds in there, so this is actually 2-methyl cyclo, hex anamine. So be careful. Remember that this really equals this is not equal to this, right? Meaning you can draw the benzene ring with a circle, you can draw the benzene ring with alternating carbon-carbon double bonds, but If you draw it with none of that stuff in there, then it's just a cyclo compound, right?
And when it's a cycle, you don't need numbers.
In this case, you don't need a number because by default, the amine is on the number 1 position because it's the most important.
And then if the M's and O's and P's.
Nope, the M's and O's and P's tell you where they are in relationship to each other, so you don't need numbers. So remember, for aromatics, if there's one thing on it, you don't need a number, right? Because it's automatically in the number 1 position. If there's 2 things, you use ortho, meta, para. And if there's 3 or more, then you have to use numbers. And that stuff just randomly crops up because they're in the computer database, and so when the test generates, who knows? You know, I used to throw on always a cyclohexane and trying to trick people, and then I realized, you know, I'll just make it random, and if it happens to show up, great. And if it doesn't, not going to worry about it too much. Okay, one other little things with amines, and this is kind of a little confusing. We also have what we call primary, secondary, and tertiary amines, but it's not like primary, secondary, and tertiary alcohols. So what primary, secondary, and tertiary amines represent is how many R groups there are on there. So a primary amine just has 1 carbon chain attached to it. A secondary amine has 2 carbon chains attached to it. A tertiary amine has 3 R groups attached to it. And then there's technically one that looks like this. So because amine has that free set of electrons, it can actually occasionally make 4 bonds, but 99 times out of 100, that 4th bond is to something that's charged, and so that has to have a positive charge. Wait, let me make sure I get my NH4+. Yeah, there has to be a positive charge associated with it. And so this is called a quaternary ammonium cation. And you don't generally see it by itself. Instead, you see it kind of paired up with something like this, where there's a plus sign and there's a minus sign. And what happens when we have a plus and a minus? Yeah, and so we call this a quaternary ammonium salt. So we will have nitrogen with 4 bonds occasionally in chemical reactions. It means we form a salt. And in fact, we've even seen it where it formed a salt with a carboxylic acid, right? Okay, let's talk physical and chemical properties. And it'll be a good review. Not chemical properties, sorry, just physical properties. We're not doing any chemical reactions. You know, I bought the El Cheapo creamer at the grocery store because I didn't have time to run to Vernal and buy some new one. It's not as good, is it? The flavored stuff is a lot better. I think it's because it doesn't have any sugar in it. Dang. That's pretty good stuff. You know, my favorite is they used to make chai, but I can't find it anywhere. That stuff, I would have just, I just drink that stuff straight. Maybe not quite straight, but yeah, the chai flavored is amazing. The pumpkin spice, that's the only time I'll go to the gas station and get stuff, is if they have the pumpkin spice one there. It's good stuff. Where do you get your pumpkin spice?
I got it over Christmas and I froze it.
Because, you know, I go to Vernal and they just don't have chai or pumpkin spice ever.
No,
The Cinnabon one is pretty good. Okay, so we got off on important topics, coffee and creamer, but getting back on topic, physical properties. So if I take a look at amides, let's give me some space. And I take a look at amines, what sort of intermolecular forces, amines, J, are available to us? Yeah, so this is capable of forming hydrogen bonds. This is capable of forming hydrogen bonds. What else? Yeah, this part on this molecule is capable of making a dipole-dipole interaction. Now here's where it gets a little tricky. This is considered a weak hydrogen bond, meaning it's actually less strong than an OH. Because there's two hydrogens, because there's that electron pair on the nitrogen, it turns out that it's kind of weak. And so in the grand scheme of hydrogen bonds, it's actually kind of a wuss. It's almost more like a dipole-dipole strength interaction. But the hydrogen bond here is actually very strong because of that carbonyl group next to it. So that carbonyl group draws the electrons away, and those hydrogen bonds are actually extra strong in an amide, whereas in an amine, because there's no what they call an electron withdrawing group, meaning there's nothing drawing electrons away from those bonds, those actually tend to be very weak hydrogen bonds. And so amines and amides to me are the tricky ones, because everything else falls into pretty much the exact order that the intermolecular forces are in, right? But amides and amines kind of break that pattern. So if we draw the end-all and be-all, meaning every functional group we've talked about, the anes, enes, and ines are kind of at the bottom, right? Technically, an ane is slightly stronger than an ene is slightly stronger than an ine because you've got a couple extra hydrogens in each of those molecules, and so the LDFs are a little bit bigger. But honestly, they're so close together that I'm not sure I would want to kind of separate them like that. What did we have slightly above them? Ether. And so ethers had a very weak dipole-dipole. And then above ethers, what did we have? We threw in esters. And that has, again, a weak dipole-dipole. And we had aldehydes and ketones. And I'll be honest, you could probably lump a good chunk of those together. Oops, I'm sorry. Hold on. I was forgetting we're in this new chapter. This is where amines fit in, because they have a weak hydrogen bond. And then we have our aldehydes and ketones. And so they're really out of place because aldehydes and ketones are dipole-dipole, right? And so that's why I say that amines kind of screw up our ordering for things. What was above aldehydes and ketones? Alcohols, they've got a hydrogen bond. Above alcohols is carboxylic acids because they had dipole-dipole plus hydrogen bond. And then above them is amides because they have dipole-dipole plus hydrogen bond. And so they're kind of the king of the hill. So amines are one of those kind of exceptions to the rule, so I'll put a bunch of little stars around it because it's out of place. Normally I would have placed amines slightly above aldehydes and ketones, and I got to be honest, these are all about the same. So really amines, aldehydes, and ketones, about the same. Amines are a little bit weaker. And we have to be extra careful because amines and amides are even more complicated than that, although we won't tend to get into it. What if I compared this amide versus this amide versus that amide? They all have LDS, right?
No, like which one is
Well, more important than that, because you're right, the size of the molecules is changing a little bit, and I could control that if I wanted to by chopping off the main chain some. But more important than that, what's really changing in that? Yeah, so notice that this can make 2 hydrogen bonds plus 1 dipole-dipole, right? But this makes only 1 hydrogen bond and 1 dipole-dipole. And this one makes 1 dipole-dipole and 0 hydrogen bonds, right? Because now there's no longer any hydrogen attached to that nitrogen, right? And so when we say amides are up at the top, we mean amides that can form 2 hydrogen bonds. After that, when it can only form 1 or 0 hydrogen bonds, it can be anywhere in that chart, and it's almost impossible to predict. So, for instance, I would never ask you compare that versus, say an aldehyde, because it'd be really tough to figure out which one is better. That would be a bad comparison, right? But, if I asked you to compare this versus an alcohol, that's a reasonable comparison. And if I ask you to compare anything in this list to itself, you should be able to figure out how many hydrogen bonds and dipole-dipole interactions it has. And so, same thing with amines. If you have an amine like, here, I guess I'll draw one, what the heck. Where you can form 2 weak hydrogen bonds versus one where we'll even keep the molecules the same size, since Jess is actually awake this morning for once. I can tell she curled her hair. Everyone looks. Well, then it maintains. I don't know. Maybe she's over her concussion too. She was a little groggy for a day or two on that. So again, here, you've got 2 weak hydrogen bonds. Here you've got 1 weak hydrogen bond. Here you've got 0 weak hydrogen bonds. And so here you would have basically just the dipole-dipole due to that thing. I mean, obviously you've got some dipole-dipole in there because of the lone pairs on the nitrogens, although with the ones that have a hydrogen bond associated with it, since that's stronger anyway, we would worry about it. And so again, amines can kind of move around in that chart. Now they can only really move downwards, right, as they make less and less hydrogen bonds. And so sometimes an amine might be more like an ether, or it might be just basically an alkane at that point. Although it's probably always going to be a tiny bit higher than an alkane, simply because it's got that lone pair on the nitrogen that can have interactions with other molecules. And so again, they're a little hard to tell. But all in all, what I really want you to remember is the main case. So amines kind of go here if they've got nothing attached to them, and amides go way up here. Now, if you do get a case where you've got something like this, remember the comparison is going to be within the same type of molecule, right? And so you can say which one has a bunch of hydrogen bonds versus which one doesn't have a bunch of hydrogen bonds. So for boiling points and solubilities, then, that means that amides have very high boiling points, right? And they have reasonable solubilities. If the R group gets too big, it doesn't matter. They can't dissolve in water anyway. And then same thing, amines are more like aldehydes and ketones, meaning that they have kind of intermediate level boiling points, and they're slightly soluble in water. But again, once they get too big, over 4 or 5 carbons, they're not going to be soluble at all. And again, I don't want you to memorize those cutoffs and say, oh, less than 6 it's soluble, but greater than 6 it's not. No, what I really want you to know is if I'm comparing 2 similar molecules and they differ by size or functional group, which one's more or less soluble. Not memorizing that, oh, all alcohols under 3 carbons are infinitely soluble. Well, great, you memorized the fact. That helps you for that specific question, doesn't help you for very much. Amides are pretty soluble as long as the R groups aren't big. And then one last miscellaneous point, because it's interesting. Amines are responsible for some of the nastiest smells in chemistry. So it turns out that ammonia, or that amine group, makes things really nasty. So for instance, some of my favorite molecules are, and I can't remember, one of them I opened up and smelled, and one of them comes in a sealed vial. It's actually sealed. You have to physically break the seal on it to open it up. But like this would normally be what compound? So 1,4-butane diamine. Its common name is putrescine. And I don't know, the word putrid is kind of what I get when I think of putrescine, because it smells like horrible. And then the next one up, if I put 5 carbons on it, you know, IUPAC-wise, we would call this 1,5-pentane diamine. Its common name is called cadaverine. Cadaverine, something like that. So yeah, really tiny. So like if something stinks, usually one of two things is responsible in chemistry: nitrogen or sulfur, because sulfur tends to stink a lot too. Let's see, do I have any other random things in there? That's under the chemical reaction stuff. Oh, well, yeah, there's lots of good amines for you guys. Read in your book. I think there's on page 698. This is really old set of notes, so that page number may not be there. I think on this homework I included a section kind of like in the alcohols, which is name important ones. But just off the top of my head, for instance, some of the important amines are things like most of your vitamins are amines. So like thiamine, nicotinamine, and things like that. Notice they have the word amine in their common name, and that's because they're containing an amine group. If you're going to be a dentist, novocaine and lidocaine contains amine groups. Let's see. Oh, some of the good ones are the alkaloids. That's what sometimes things with amine groups are called in them. Nicotine has an amine group in it. Methadone, you guys know what that is? You know what cocaine is? Methadone is, I think, if I remember right, I might get this reversed or something, but methadone is what they give you when they want you to get you off of cocaine. Now, maybe it's heroin. I don't keep track of my drugs too very well. Methadone might be the treatment for heroin. I don't remember, but it's basically a less addictive version of that compound. Any of your amphetamines that you take for depression, narcolepsy, obesity, any of that stuff, or just to pop them for speed, you know, that they contain that group. Any of your barbiturates do, tranquilizers, Prozac, all of those things contain amines and or amide groups in them. So there's a lot of compounds and a lot of drugs that contain these things. So when you go in dental hygiene, for most of you, go ahead and take pharmacology, you should be seeing lots of amine groups, right? And you should be recognizing them and going, oh yeah, that makes sense. Okay, that's it for that. One other thing I wanted to point out sort of in terms of review is how to answer boiling point, melting point, and solubility questions. Now, it really depends on how I word the questions, meaning on some tests I've actually literally said circle the molecule with a higher boiling point and just left it like that and not included the word explain. But if I do add the word explain, then that means I want you to say things like mention the fact that the boiling point is proportional to the strength of the intermolecular forces or the attractive forces between molecules. It means I want you to mention functional groups. And so what I mean, for instance, is I don't want a simple statement, you know, let's just pick a nice easy one like this. Which one has the higher boiling point? 1 or 2? Yeah, the first molecule I drew, right? I don't want you to simply say alcohols have higher boiling points than alkanes. I mean, certainly that is a true sentence, right? There's nothing really wrong with it. And if I phrase the questions right on the test, I actually get kind of what I really want. But I also want you guys to recognize that there's a lot of different levels that you can answer that question at. You can simply circle it, right? That's level 1. Actually, we call that level 0 because that's just a guess, worst case scenario, right? That's not much more than a guess, to be honest. That shows me that at least you recognize what an alcohol functional group looks like and an alkane functional group looks like, right? But I could have just as easily circled the alkane and written alkanes have higher boiling points than alcohols and show that I have no knowledge even though I wrote a sentence, right? But if you start getting into things like, you know, mentioning that the alcohol functional group has a higher boiling point than the alkane because boiling point is proportional to the strength of the intermolecular forces, and alcohols are capable of forming hydrogen bonds, and hydrogen bonds are certainly stronger than London dispersion forces. Now if you use enough of those words kind of in the right sentence, in the right order, in the right spots in the sentence, now I really start to believe you guys that you really truly understand what's going on and you simply haven't memorized that alkanes are greater than that. In fact, you know, the 0th order answer is simply to memorize that list, right? And not necessarily understand why that list is that list. So add things like that. Talk about functional groups. Talk about the differences between the intermolecular forces. Talk about hydrogen bonding and things like that. If I phrase the questions right, I tend to phrase questions like, for instance, the solubility in water decreases as the length of the alkane chain in a molecule increases. Why? Yeah, so if we're talking solubility in this question, you know, if I simply say circle the molecule that's more soluble, then you circle this one, right? But if I phrase the question, and then a lot of people simply said short alcohols are more, short is better than long. Well, that's great. You memorize that factoid, because that's what it really is at that point. It's a factoid. At least the way you wrote the sentence, to me, indicates that you memorized a factoid. If you can make a complete sentence with all the words in the right spots, then I believe you. If you can simply say that, you know, both molecules have a soluble OH group because it can form bonds with, or form, doesn't form bonds. That's one of the key words I need to mention that we need to, because it can interact with, let's say it that way, interact with H2O via a hydrogen bond, but the alkane parts are insoluble because London dispersion forces do not interact with hydrogen bonds, dipole-dipoles of water. And you could even use the word polar and nonpolar there if you wanted to say something, you know. Then the shorter molecule is more soluble because it has less insoluble parts. Now there's a lot of ways you could phrase that. But words I want you guys to stay away from is never say that you're going to break apart the molecules. Because what does that imply you're doing? Well, it might mean that you're saying, I'm going to break, oops, I should at least draw a hydrogen bond properly, right? It might mean that you actually really think you're breaking the hydrogen bond, right? In which case it's okay. But equally, I've had many, many students make it obvious that they really think I'm breaking apart a bond. So when we say break apart the molecules, we've got to be really careful, right? I mean, combustion breaks apart molecules, right? I mean, it literally snaps them apart and rearranges them and stuff. And so there are certain other phrases that if they're used improperly, they might mean one thing to you, because you might really think that you mean number one, where you're breaking and separating the molecules, right? Whereas I say that it's unclear whether you imply that you're breaking the hydrogen bond or you're breaking the OHs. So maybe a better way to say it is, instead of break apart the molecules, is break apart the intermolecular forces holding the molecules, or to separate the molecules by breaking the intermolecular forces, meaning specify exactly what you're breaking, which is not the bonds, right? And so I do have to be honest, sometimes I'm awful picky on these explanations. That being said, you never know on the test whether I'm going to ask the level 0 question, which is simply circle one of the molecules and guess, the level 2 question, which is at least include a short fragment or sentence, or the level 3 one, which is explain this as thoroughly as possible. So here's my theory. What's the best answer? Number 3, because if you explain it as thoroughly as possible, I'll believe you. Now you have to be careful. If you don't really understand it, or you are a little sloppy with the English language, you can dig yourself a hole too by saying you break apart molecules and things like that. So I'm kind of warning you what the bad phrases are, hopefully. Let's see. What other things did I want to mention? We've kind of talked about just about everything. Oh, there's a typo. Oh well, that's okay. Yeah, that's the one thing I wanted to mention from the homework. I guess the other thing I wanted to mention on the homework is we did ask a question, which was, given a list of molecules, which one can form hydrogen bonds? And I realized that the question was a little tough because I had molecules like that, molecules like this. And since this was not in the carboxylic acid and ester chapter, we didn't include any carboxylic acids and esters. So I think the only other thing I had was maybe like that. I might have thrown in something with a carbon-carbon double bond. Which one of those molecules are capable of forming hydrogen bonds? We'll just go through them in order. Number 1, right? Number 2? Number 3? I'm going to put a little dotted box around these two. They can interact with something via their dipole-dipole to another hydrogen bond, right? But the question I was trying to say is that, can they themselves form a hydrogen bond? No, but they could interact with water, right, via what might be considered a hydrogen bond. And so what I've rephrased the question on the homework is, given a list of molecules, which ones can form hydrogen bonds between themselves? Meaning, you know, 2 alcohols can form a hydrogen bond like this, right? Where they kind of line those up. And don't forget your partial positives and partial negatives and all that good stuff when you're drawing lots of pictures. But, you know, if I have 2 of these, oops, like that, you know, that really is a dipole-dipole, right? But that can interact with water in what we would kind of consider a dipole-dipole / hydrogen bond. And again, some books will call that a hydrogen bond and some will not. And so really the only true answer is the alcohol, if I phrase the question properly, right? Which I did. I went back and changed the homework. Now, of course, I didn't check if I changed the homework in chapter 24 or if I changed the homework in chapter 25, but such is life. So, let's see. Today is Wednesday, right? Homework 24A was due. That's just naming, right? And then on Friday, we should expect homework 25A is due. And I'm going to mention, and I don't know, I have to really look on those. You may or may not be able to do them, but you should be able to do at least half of 25 and 24C and 25C, usually. Meaning, sometimes there's questions on there about reactions and visible clues and stuff, meaning I consider that 25C homework miscellaneous. So try to get those 2 homeworks done, because you know that on Friday you're going to be assigned the reactions from chapter 24 and whatever we cover in chapter 25. And so this weekend will be reactions for you. So what I really kind of recommend is, yeah, I know you're studying for the test on Thursday. I probably should have just put the test for today, but I figured we'd give you the extra time that you get on a lab day. is make sure that you've mastered those namings and practice that before the weekend so that then next week you're focusing only on reactions, right? And all of the solubility crap and the boiling points and melting points and that miscellaneous stuff, I got to be honest, I hope by now you don't even have to study it because you've already seen it. You'll have seen it for 2 tests, and so it should be hopefully in your brain, meaning it's not too much new each time. It's just the same thing with new functional groups. I don't know, you guys have any questions? So I'll be available in my office starting sometime in the early afternoon. I'll probably go and get lunch, and I need to stop at the bank, so I probably won't be back till like 12:30 or something. I know a lot of you guys have Todd's lab, so between 2:30 and 5, come by and ask questions, and if we really, and then I guess Thursday morning, I don't know when you guys have classes, but I'm free Thursday morning from I think 8 o'clock till 10:30. So you guys can come in early on that. And I'm usually here by 7-ish. And so, you know, come in and ask questions early on that. And maybe tonight, I don't know. You can text me if you're desperate, and we'll see where I'm at. I may have drank too much wine to give you a coherent answer anyway. Oops, I said that on tape. Oh well, everyone knows I'm an alcoholic. It's not a big secret. Why? Gosh, it's sad. Now I'm trying to think of the last time I had a beer, and I can't remember. Yeah, I can't even remember the last time I had since then. That was like last. I'll be honest, I probably